Equilibrium and free energy. A single electron has a negative charge equal in magnitude to the elementary charge, E, which is 1.602 times 10 to the minus 19th coulombs. If one electron falls through an electric potential, E0, it releases an amount of energy given by minus E times E0. A mole of electrons has a charge of 96,485 coulombs. Faraday's constant, named after the famous physicist Michael Faraday, is the charge per mole of electrons. If n moles of electrons fall through an electric potential E0, they release an amount of energy given by minus n F E0. The change in Gibbs free energy, delta G0, which we covered in the last unit, for a redox reaction is equal to the change in the energy of the system under standard conditions. It is also equal to the change in the energy of the moles of electrons that fall through the electric potential of the reaction. So we have delta G0 is minus NF E0, where N is the number of moles of electrons transferred in the balanced redox reaction, which is balanced for both species and electrons. F is a constant, the Faraday. E0 is the cell potential. Standard conditions, 25 degrees Celsius, 1 atmosphere, and 1 mole. 1 Faraday is 96,485 coulombs per mole, or joules per volt mole. It's important to note that N is the number of electrons which appears in each half reaction equation once the pair of half reaction equations are balanced, both for species and electrons. That will usually be the first step in using this equation to find delta G0. The goal is to find delta G0 for a balanced redox equation. In earlier cases, like in the ideal gas law, N can be given any arbitrary value consistent with the other variables. In this case, the value of N is determined by the balanced half reaction equations. In addition to providing the means to determine delta G0 from delta E0, or vice versa, the formula also shows that delta G0 and delta E0 always have opposite signs, or are both zero, since N and F are always positive. For a spontaneous reaction to proceed in an electrolytic cell, well, we've studied this, delta G0 has to be less than zero, but that means now that delta E0 has to be greater than zero. After determining the sign of one of these, you can determine both of them. You just swap the sign. Example 1 for E0 and delta G0, we have aluminum here and bromine. Determine the number of moles of electrons transferred in the balanced redox equation, determine E0, and then determine delta G0. Determine the number of moles of electrons transferred in the balanced redox equation. Notice they're not asking us for the balanced redox equation, but we know that you have to have the same amount of electrons transferred from one to the other. So we see this is 3, this is 2. That's not going to work. How do we get them to be equal? Multiply the top equation by 2 and the bottom by 3. So when we do that, this is what we have. Now remember, this doesn't affect the SRP since this is an intensive property. It doesn't depend on how many electrons you have. So our answer to this question is 6 moles of electrons will need to be transferred. So N is equal to 6 moles of electrons. Determine E0. Well, E0 of the cell is E0 of the SRP of the cathode minus E0 the SRP of the anode. Now the anode has the most negative SRP. So that's right here. Aluminum is the anode, and that's going to be negative 1.676. The cathode then is the bromine, and that's 1.065. Carry out the math, and we get 2.741 volts. Determine delta G0. That's going to be minus NFE. Here's the 6 moles of electrons that we came up with the balanced equations. Here's our Faraday constant. And here's the voltage that we found, or the E0. Multiply everybody together, you get delta G0 is minus 1,587 kilojoules. Example 2, very much like example 1, just 2 different equations. determine the number of moles of electrons transferred, determine E naught, and then delta G naught. Determine the number of moles of electrons transferred in the balanced redox equation. So once again, we need the same electrons for each half reaction. So this one has 2, this one has 4. So what do we have to do to get those electrons equal? Just multiply this equation by 2. So here it is, multiplied by 2. So we now see that we have 4 electrons transferred. So it's not really 4 electrons, right? But 4 is our coefficient. So 4 moles of electrons will need to be transferred. So this is the value of N. Determine E naught. Here is our equation. Which one is the anode? That's the most negative or at least positive. So that's going to be hydrogen here. So that's 0.0. And then, of course, the other one will be the cathode, 1.23. E naught cell, 1.3 volts. Determine delta G naught. Well, that's equal to minus F times E. F is the Faraday constant. Here's our 4 moles. Here's the Faraday constant. And here's the voltage. And we get delta G naught of minus 474 kilojoules. More about this example. The negative value of delta G naught shows that this is a spontaneous reaction. Hydrogen and oxygen brought into contact with a spark to start the reaction come together to form water, releasing significant energy. This energy is also released when carbohydrates are digested in biological systems that fuel life. Carbohydrates are formed, capturing that energy by the process of photosynthesis, which converts sunlight into chemical energy by driving this reaction in its opposite non-spontaneous direction. This is the basis for life on the surface of Earth, so it's very important. We now store energy in the form of hydrogen gas by using electrolysis to run this reaction backwards, as you'll learn later.